Welcome to the solution to the Regents Physics Springs and Simple Harmonic Motion problem set. Problem number 3. All right, here we go. We have a graph that shows force versus elongation for a spring whose spring constant is 5.00 newtons per meter. You can see being force versus elongation that we have force plotted on the y-axis, elongation plotted on the x-axis. And let's take a look at what they want for A. A says on a graph of force versus distance, in this case elongation, the area under the line of the graph is equal to the work done on the spring. Calculate the work done to stretch the spring from a length of 1 meter to a length of 4 meters. To do this, find the area of the shaded portion of the graph. Make sure you use the numbers on the axis and show your work. All right, to get started here, most of us would take the area of the shaded graph and we would divide it into two parts. We would divide it into this triangle and this rectangle. That gives us our area equal to 1/2 base times height for the triangle portion plus the length times the width for the rectangle portion. All right, here we go. So A equals, for the triangle, we have 1/2. The base is 1 to 4, so that's 3 meters. And our height is from 5 to 20, so that would be 15 newtons. Plus, our length, again, would be the 1 to 4, so that would be 3 meters. And our width of our rectangle would be from 0 to 5, so that would be 5 newtons. We go ahead and we add all that up, do our multiplication first, and then add those together, and we get 37.5 newtons times meters, which we recognize as the same unit as joules. This also makes sense because we were told that the area is equal to the work done, and we know area units of work is joules. All right, now next in B, they tell us the formula for the potential energy stored in a stretched or compressed spring is given by PES equals 1/2 kx squared. In B1, they want for the spring graph on the previous page, which is right above here, calculate the potential energy of the spring when the elongation is, and they want a calculation for when it's stretched at 1 meter and when it's stretched at 4 meters, just like in our graph here. All right, so for the 1 meter stretch, we'd set it up. PES equals 1/2 kx squared. 1/2, we were told up above, the spring constant is 5.00 newtons per meter. And the stretch from equilibrium is 1 meter squared. We go ahead and do the calculation here. 1 squared just stays 1. 1/2 of 5 is 2.5 joules. We now perform the same calculation for the stretch at 4 meters. 1/2, 5 newtons per meter times 4 meters squared. 4 squared is 16. Half that is 8. 8 times 5 is 40 joules. Okay? All right. Moving along. Part B2 here. Calculate the change in potential energy when the spring is stretched from a length of 1 meter to a length of 4 meters. Well, a change is final minus initial. So delta PES equals PES final minus PES initial. Well, our final PES was 40 joules, the stretch at 4 meters. Our initial elastic potential energy is 2.5 joules, the stretch at 1 meter. Subtracting the two, we get an answer of 37.5 joules. And lastly, part C asks, how does the work calculated in part A compare to the change in potential energy calculated in part B2? Well, going back up here, our work from our area was 37.5 joules. Our change in elastic potential energy is 37.5 joules. So our work done is equal to the change in elastic potential energy. What physics concept indicates that this should be true? Well, you might recognize this as the work-energy theorem. So the work-energy theorem states that the work done to stretch the spring is equal to the spring's change in elastic potential energy. By the way, you're going to be testing this also in the lab. All right, that'll do it for this problem, number 3. More to come as we do number 4 together in class tomorrow.